worry about inhomogeneities of the qubit frequency. It just doesn't happen. Okay. So with that background, I want to explain how we can manipulate these spins and how we can entangle spins leading up to engineering interesting Hamiltonian that have interactions between these spins. So the picture, and I in this platform, I tend to muddy the waters between quantum computing and quantum simulation. To me, they're really the same thing. Quantum simulation can be a little easier, and I'll get to that in this platform, but they involve the same physics of how we get spins to interact. And it's always through an optical dipole force, a spin-dependent optical dipole force. And because the ions are charged, that maps the spins to the motion, and the motion is naturally coupled to Coulomb interaction. So, if we want to, for instance, entangle any pair of these ions in this chain here, we apply optical tweezers to the target atoms that we want to entangle. And this, due to the selection rules, I won't get into details here, it's pretty simple. It turns out that these tweezers are counter-propagating beams that you absorb from one and you emit into the other. These are Raman transitions, and that conveys a force. But the force is spin dependent. So for instance, if this fourth atom is in spin up, the atom will move up a little bit. If it's down, it'll move down. And so the way you can see how you make entanglement is simply by considering the Coulomb interaction between these two atoms. If they're both in the same state, their individual pairwise Coulomb interaction is exactly the same because they're the same distance apart. But if they're in the odd states, up, down, or down, up, they're a bit further apart, and this defect in their Coulomb energy gives us an energy shift that's spin dependent. And if you look at the four possible states of those two spins, only the odd parity states pick up this phase factor. And when you set the phase factor, for instance, to pi over 2, by judiciously choosing the time that you apply the force, how much power is in that laser beam, which gives you a deflection here of the atoms, which is just a few nanometers. Yeah, when I do this, it's way out of scale. The separation between atoms is microns, but this little displacement is a few nanometers, deep in the harmonic approximation. And when that phase is set to pi over 2, this is called a phase gate. It's equivalent to a controlled knot gate. It allows you to fully entangle these ions. And this is based on work from long ago. Soraki Zoller, a different version of this. Moore and Sorensen, you may have heard those two names together. That's basically what I'm describing here, these spin-dependent forces. And the native interaction we have is this Ising interaction, which is basically this evolution here. It's in the X basis of spin, not the Z basis. That's a little bit of the trick here. Another little trick that I won't dive into too much is that the time required for reasonable laser powers to get to pi over 2 here is much slower than the normal mode of vibration, the small oscillation frequency of these ions. So when you pluck these two ions, they all feel that motion. So you really have to consider all of the normal modes of motion. If you're designing quantum gates and you want them to be fast, what we do there is laser pole shaping so that all the normal modes cancel at the end of the day. But if we want to do quantum simulation, we don't want to excite the motion at all. So the force that we apply is very far from resonance. So we're driving a particular mode of oscillation, or all the modes of oscillation, very far from resonance. And in that way, we only virtually excite the motion. Okay, a lot of words there, but we end up with a pure spin Hamiltonian here. And this is what we're going to use to make the simulation. Now, I said earlier that simulations are a little easier than quantum gates, partly because the optics, we often want to illuminate all of the ions at the same time. And when we do that, we have an Ising coupling between all pairs of spins. It's not just nearest neighbors. And to see how this works, there's some math you have to get involved with because the ions are excited through their normal modes of motion, just the classical harmonic modes of motion, and you have to consider the spectrum of that motion. And so in this picture, I'm depicting the sideband spectrum of harmonic motion. So what do we have here? I mentioned that we have counter-propagating laser beams, and they have a beat node. And when that beat node is right at the hyperfine splitting, we can flip the spin. So that's sort of what we would call rotation, the individual spin, a sigma x operation or a sigma y operation of the spin. But because the ions move harmonically, the laser acquires FM sidebands. So we can tune the laser to be near the upper sidebands or the lower sidebands. And because there are lots of ions in the chain, there are lots of modes. And due to the Coulomb interaction, these modes are separated. So, there's always an interaction between modes causes you to separation. And we need to know what those are. This is just classical physics. We can calculate all these things. And we tune our laser beam, as I mentioned, detuned from all these normal nodes. So now, in an integrating way, I can motivate this expression for the Ising coupling between spin I and spin J. Well, it's a sum over all the modes that mediate that coupling. And now you can see why it's long range, because normal modes are long range, right? Like the tilt mode, the ions that are furthest apart actually participate most in that mode. The B matrix, these are the participation matrices of normal modes. You get classical mechanics here. The eigen, this is basically the eigenvector between ion I and mode M. We sum over all modes, and because we're talking about I and J, we need to look at both participations in mode M, and we sum over those modes. Because we're detuned from those modes, we have a detuning in the denominator. You can think of this as coming from perturbation theory. Many ways to look at that. And so this equation, there's not much to say. I don't have too much intuition there. But it turns out, if you plug in the numerics for a linear chain, it turns out that the Ising coupling roughly follows a power law, an inverse power law. That is, the interaction falls off like 1 over a power distance. And in theory, we can vary that power between 0 and 3. 0 means that it's uniform. All spins talk to all other spins with the same strength. That would be the case if we had very low detuning. In other words, this mu parameter is right at that top mode, which is the center mass mode. And when we do that, the center mass mode is the only one excited, and the center mass mode is obviously uniform. And that gives us alpha equals 0. If we detune really far away, then we have to consider all of the modes. And it turns out that you get this 1 over r cubed, sort of dipole type fall off. In practice, we can't go to 0 or 3 for technical reasons, but we have some tunability in between. So that's kind of an interesting knob. We can tune the range of this long range interaction. So we're going to exploit that for all kinds of experiments. I'm going to now give you a little bit of a background on it. Oh, we can also apply this is trivial, we can apply an effective magnetic field in addition to the Ising model in Ising couplings. Now, to make it interesting, we want the magnetic field to be transverse to the Ising coupling so that this term doesn't commute with that term. And then we can get phase transitions, things like this. This is easy. We simply add a beat node. You'll notice in the animation, there's a new beat node right at the spin flip frequency. And it carries with no phase shift difference, because of the I in the, I won't get into details there, we end up with a natural Y field here compared to the X Ising couplings. Okay? And by the way, this is sort of recent, the last year or two. You might wonder, why are we limited to just bilinear poly spin operators, XX or YY or ZZ? Well, it's not because the Coulomb interaction is just between two charges. That's not the reason. The reason is more subtle. It has to do with the normal modes that mediate the interaction. A and A dagger. These are the harmonic oscillator annihilation and creation operators. And the reason we only have bilinear spin operators is that A and A dagger commute to a C number, to 1. And so therefore, higher order spin operators just don't appear. Well, we can change that by, instead of doing a spin-dependent force, when we apply a spin-dependent squeezing operator, I won't get into details there, but that's an A dagger squared and an A squared type of force. And it's actually easy to do, even in software. You simply change from tuning near the first sideband to the second sideband. I won't get into details there, but it's a very expressive operation that allows you to generate polynomials of Pauli matrices. So you can get n-body interactions, accompanied by many others, and we can control that, the amplitudes there. I won't talk about this anymore, but it's very interesting for quantum computing, for little mini circuits that can be optimized for that when your algorithm has a particular structure, but also for quantum simulations when you really have to have a four-body interaction. We're learning that we can do this with the trap axis. Okay, so now diving into the laboratory, and if you see me talk, I always sort of distribute the bad news, good news experimental plot here. This is a typical ion trap lab that looks like a mess, and nobody would want to work in that lab. Certainly not to scale up the system to many more spins to do something interesting. But this is a physics laboratory where we have flexibility on absolutely everything. And most of the real estate here is devoted to the optics, the lasers, and distributing that light to the ions. The ions are in a chip in a vacuum chamber that you can't even really see. It's a very tiny volume here. But the good news is we know if we want to freeze some of this design in place, it's very easy to do. And over the last few years, what you saw in the last slide is pretty much packed into this couple of meter cube box. And the box is open maybe every quarter. So everything that needs to be adjusted is done inside. And what's inside there is a vacuum chamber with the chip that I showed you and a bunch of laser beams. And anything that we need adjusting is on motorized mounts that we can automatically adjust from the outside. I'll also mention my colleague at Duke, Trixie and Kim. He's very much the engineer interested in miniaturizing things and making them much more reliable. He's been working with Cold Quanta for many years on even the miniaturization of the vacuum chamber. And here it is. It's sealed right on the chip with an indium seal. There's a tiny ion pump that's not shown in one of these appendages. But things are really small, and the footprint of our system has nothing. The money shot here is really observing the space transition, and theoretically on the right-hand side, we're plotting this observable here is once again, the mean squared magnetization along x, and this is the transverse magnetization along z. And we have the different energy states that we measured, and different values of the transverse field gene variables. So that's what Alex likes to use, G over J here. We can see, theoretically, we expect this sort of second order phase transition to occur right here, where we have the ferromagnetic ordering down here, and then out here is unpolarized. And the data matches very well with the theory. A little less so on the transverse magnetization. We're still sort of understanding that as work in progress. But what's interesting here is it seems to be the first observation of signatures of a 1D phase transition. A related experiment that's following on the slide here, several months ago, we observed continued symmetry breaking in this 1D chain. This is a collaboration with Alexei Gorshkov, which will appear in Nature very soon. And my chairman is telling me I only have a few minutes left, and I really wanted to talk about your experiment, which is a different type of a phase transition, where we introduce measurements in a circuit, and with the density, as the density in the measurements gets increased, the amount of entanglement in the circuit goes down, and that's actually a phase transition, called a measurement-induced phase transition. It's akin to percolation phase transitions, and it's very deeply related with error correction. Because if the error rates are low enough, you still see full entanglement. You see in the sense of, say, volume blocking. Whereas if the error rates are very high, then you see area blocking. The character of entanglement as a phase transition. This is really akin to what happens in error correction with fault tolerance. There's a phase transition of being able to handle error. I do want to make an adversity here for a great collaboration between INQ and the University of Maryland called QLab. There's one whole machine that INQ is working, that Maryland researchers can use, not just in physics, but all across the university. This is one example of that. The next generation of this experiment has to do with distillation of magic states by inserting errors of various intensity in sort of a random circuit here. And again, Michael's really spearheaded this work the last few years. Okay, so I'm just going to skip right to the topological. We simulated SSH Hamiltonian. I'll give you the 2-second version. This is a 22-ion chain, and we show that edge states, when we excite them, they maintain a much longer life than the bulk. And the bulk, as expected from this SSH Hamiltonian, what you have is alternating nearest neighbor isotopes. So, and with that, I'm way out of time. It wasn't clear that a half hour, an hour, but I think that's Quantum Center, which is a fairly unique institute where we're not necessarily doing quantum information science or atomic physics or platform physics. We're doing full stack, vertical, a vertical organization of quantum computing from the very top, those that are interested in algorithms or simulations, to those like me on the very bottom, who are atomic physicists and engineers. And we have several systems, 5 or 6 IO-trapped quantum computers that are fully programmable. They have different features and bugs, and we want to model ourselves as sort of a user facility where we can do problems in all walks of science. And this is something, I know there's lots of companies building systems, including a company I co-founded at IonQ, but those companies need to create commercial value. This uses very advanced quantum computer, quantum simulation technology for science, which is something companies probably won't do so much. So if you have an interesting application, if you want to design a particular Hamiltonian, please talk about it. And with that, I will just leave the slide of current members of my group in bold here. A few of them are in the crowd. I mean, Emma and Key are in this conference, and many others you can see remarkably good at companies across the country. And I would like to acknowledge support from the NSF STAT program in particular for this, but also IRBA and the DoD agencies. Thank you.
Great. So yeah, just our set talks I guess should be 25 minutes, and then there's 5 minutes for questions. Thanks for the great talk, and yeah, let's take questions. Anybody who has a question, I can try and run up, or you can come up to the 2 microphones in the front of the room. So, you can just feel free to line up.
Yeah, thanks for a great talk. I think you covered a lot about how ion traps are used for a lot of NIST quantum simulations. The question I have sort of pertains to how you see the prospects for scaling them to full fault tolerance. So in particular, we have seen a number of experiments that are sort of demonstrating very small error-correcting codes on ion traps, but one thing I really haven't seen much of is attempts to look at, say, the resources required to realize classically intractable quantum simulation for application within fault tolerance on an ion trap. That's something that's kind of become common on other architectures like photonics or superconducting or even topological. So I'm curious why that is. You think it's sort of a cultural thing with ion traps that they're sort of not looking at that, or do you think there's like aspects of the architecture that aren't worked out to the point where doing that makes sense?
Okay, good question. I can't answer that for about a half hour, but I'll skip to the chase. The errors that we have in ion systems, they're not T1 or T2. They're not unknown. 98% of the errors we have are coherent errors. They're control errors. So the last thing I would try to do is go blind with a fault-tolerant error correcting code. That's basically, that's sort of being ignorant. With ion traps, we don't need to do that yet. We probably won't need to do it for another decade. So, our group and many other groups have indeed encoded logical qubits, but they're demonstrations. I don't think we'll ever use them. I think we will be able to mitigate errors to a level where we can get well beyond what can be calculated. That would require error rates of 10 to the minus 4, 10 to the minus 5. And that means you should only need if you have 100 qubits, you need about 10 to 4 of those. And that's right around where native errors, like laser scattering, real T1 and T2 happen. And we're not there yet to do that. So it is a cultural thing in ion traps. We don't need it. We just don't need it right now. And I think when we're able to find applications without error correction, I think there will be many more resources that will be poured into this technology. Nobody's done the engineering for ion traps like they have in any solid-state platform, so we're just scratching the surface. But when those resources come in, then we can maybe think about fault-tolerant error correction, but that's a long way away.
Great discussion. So I guess we're a little bit over time, so I think there's, of course, time for more discussions. If you said you could go on for a long time with this. So, yeah, let's welcome the next speaker. So it's Bucky Baker from Princeton University. He's going to tell us about it's a new title, Directly Imaging Spin Polarons in a Kinetically Frustrated Hubbard Model. Oh yeah, there's still lots of room in front. People are saying that.
And for bringing us together in this wonderful venue to discuss conservation. So I'm going to be talking about just one of the topics I had on my abstract to keep so more comprehensible. If you want to hear more about work from our molecular microscope, we can discuss it in Alright, so to give you a brief overview of the work we do in my group, we are interested in doing quantum many-body physics with ultra-cold gases of atoms and molecules. So what we do is we basically engineer these Hamiltonians, which are theoretical Hamiltonians, which can be used to describe electronic models in condensed matter physics. So they describe materials like these high DC superconductors or Monroe materials or quantum magnets, where in these materials you have these strong correlations between the electrons, which give rise to emergent phenomena, to new types of phases, with exotic properties that might be useful for technological applications. And we are interested in understanding these materials, so these models from a microscopic point of view, to better engineer their properties. So most of what I'll be talking about today is going to be relevant to these Monroe materials. Okay, so the platform here is called atoms in optical lattices. Optical lattices are basically potentials that we create through the interference of laser beams in the lab. And in this quantum simulation, basically the atoms are playing the role of the electrons in a solid, and the optical lattice is playing the role of the ionic lattice in a solid. So we can think of this as an enlarged model for condensed matter physics, where we blow up the system by about 4 orders of magnitude. The length scale is here on the order of the wavelength of light, so about half a micron or so. And the benefits of this platform are, first, the Hamiltonian we write down for the system is very well understood from the microscopic level with the precision of atomic physics, unlike the crude models that people use for condensed matter systems. And furthermore, we have control over all the parameters of this Hamiltonian, often in real time. So for example, you can control the tunneling of the atoms in the optical lattice, changing the laser intensity, or you do the atoms or the chip. It's really the optics that controls everything. So in building this system, we recognized that most of the day we weren't doing atomic physics, lasers, or anything of the like. We were doing calibrations, running circuits, running algorithms, running quantum simulations. And we've been very blessed by having a huge number of collaborators throughout the last several years that have been interested in running simulations, running circuits. And what's very interesting is that many of these collaborators don't need to know anything about atomic physics or lasers. They can say, just, I want a simultonian. I want this circuit, please run it for me. So we've been in a position to be able to do that. And I'll also acknowledge my colleagues, now Duke, Norbert Linke, Marco Cetina, and Chris Knoll. And all 4 of us with a few others are really leading the charge, building other versions of this type of system, scaling to larger sizes, and working with collaborators to run interesting physics simulations and circuits. I'll give you a few examples. I'll probably run out of time. But one of them from a few years ago is connected to the concept of quantum scrambling, which is a sort of a new term in the last 5 or 8 years or so. So scrambling is a property of a unitary, quantum unitary, and in a sense it's more than entanglement. It's entanglement at all depths, if you want. And the connection to quantum gravity, I'm told, is that quantum models of a black hole involve fast scrambling. So if you put a qubit into into a black hole, and you believe somehow that black hole is a closed unitary system, then that qubit gets entangled at all depths with all of the other periods of freedom of the black hole. Or so Ben Yoshida tells me, and Lenny Susskind and so forth. So they proposed to us, especially Norm Yao and Ben Yoshida, to run a very small circuit of just 7 qubits. And this circuit would be a detector of scrambling. Now, the idea here in the circuit, this is a standard space-time diagram, so the 7 qubits here, time going from left to right. Now, the unitary here is only a 3-qubit unitary. And you need at least 3 qubits to talk about scrambling. With 2 qubits, scrambling and entanglement are the same, there's only one depth of entanglement. With 3 qubits, there are entangling unitaries that are not scrambling. So scrambling is something that's a little bit elusive to detect, and you may have heard of the term time order. What's the acronym? OTOC, out of time order correlator. You need to evolve qubits forward in time and backward in time to make the correlation, and that's really hard to do, especially in the face of decoherence and so forth. So this circuit is a little stronger than an OTOP because it allows you to unambiguously detect whether your system's scrambled. So here's how it goes. You have some input qubit. This should be an arbitrary state. In practice, you put many different quantum states into that rail. All the others are initialized. There's a bunch of icing gates that allow us to entangle. Let's see, 2 with 5, 3 with 4, 6 with 7. Then we apply the unitary that we wondered if we're asking does it scramble or not, and we apply its inverse, its Hermitian edge recall. And then we measure Bell correlations, Bell state detectors on any of these pairs. And it turns out, and this is kind of amazing, if the unitary scrambles, then this quantum state is teleported to the seventh rail, if and only if U scrambles. So you can think of this as simulating 2 black holes, one going forward and one backward in time with 3 qubits. Yeah, that's a joke. But the unitary we program, I won't get into the details of the circuit, but it's a circuit that has a parameter here, theta, that we can tune. When theta is 0, there's no scrambling, we know that. When theta is power 2, it scrambles maximum. And we basically varied that angle, and for a bunch of different input states, we calculated the teleportation fidelity, and if it's above a half, that means that there's scrambling. It should have gone all the way to 1, but yeah, we're good at showing it. So it's a laboratory. These are fairly deep circuits, and they're, each gate is maybe 98.5% clean. There's a lot of them, so we were pretty happy with the 0.75, even the known errors. Okay, so what we're very interested in doing to follow up on this is a related circuit where we apply U and U star in this case. I won't get into the details here, but what's interesting is what we want to input on these 2 branches is a so-called thermal field double state, which is a pure state, very hard to make these days. It's a pure state of 2 subsystems, and when you trace over one system, the other system is a thermal state with no coherence. So it's like a 2-mode squeeze state, if you want to think of it that way. And when you make a state like this and go through, there are analogies to teleporting through a wormhole. Again, I'm not making up those words. This is sort of the analogy. So this is work in progress. Same circuit. Okay, so let me go through some examples of what we can do with this simulator in the analog mode, if you want. Not a gate type simulator, but when we globally apply light to all the ions. And this one was from a few years ago. It's a so-called dynamical phase transition. And I've drawn here the Hamiltonian that we engineered. You've seen this already. The inverse power law Ising coupling with a transverse effective magnetic field. And this experiment actually is really easy. We prepare all the students along the x direction. So we use a pulse to prepare up plus down to the nth power. If you think along the z direction, that initial state has all spin states in it. Up plus down to the nth power has pretty much every state in the z basis represented. Then we turn on this Hamiltonian for some amount of time, And then we simply measure the spins at some time, and then we do the whole experiment again and increment the time. We're just measuring dynamics here. So the first thing we might do is measure the total magnetization along X of the spin chain. And what we're varying here, so this is the magnetization scale between 1 and -1. That's spin up along X, spin down along X. And over time, we see for relatively small values of B over J, nothing very exciting happens because B is small. We're already in an eigenstate of this, so there's very little evolution. And you kind of see that. There are some wiggles because there is some dynamics to the Z field. But at much higher values of B over J, over the nearest neighbor Ising coupling, the dynamics is distinctly different. And in this case, the field is bigger and the spins are all along the x-axis, so they basically mutate around the Z field. And we sort of see that. And this is really decoherence, but we have spins of different couplings, so it's sort of a mess. But these are definitely different types of dynamics. We wouldn't call it exactly a phase transition. When you go to intermediate values, it's sort of a smooth. Next, we can plot the correlator. Remember, we have access to every spin. In a single shot, we can mention this. We can measure in a single shot every single spin value and its correlator. So this is a sum over all two-body correlators normalized to 1 over n squared, because they're n squared pairs. And here we're plotting for different numbers of spins in the chain this two-body correlator average over all correlators as a function of B over J. And we see that there's sort of a dip, and then it kind of comes out. At higher numbers of spins, the dip is a little more defined. And this dashed line is the simple theory when you think of this thermal equilibrium line. And it sort of breaks down, not surprisingly, because we have massive entanglement going on in the system. Again, I wouldn't call this a phase transition. If you go to infinite number of spins, this should be a logarithmic divergence, and you might call it a phase transition. But as I said, we can measure n-body correlators. So this is a very funny measurement of an n-body correlator. It's the size of the largest domain after we apply this Hamiltonian. It's sort of a weird order parameter if you want. But as we increase B over J, we see that there's sort of we see big domains that it's similar to see just from these 4 data points, but we see sort of a minimum of the domain size, the maximum domain size, as a function of B over J. And the take-home point here is this is 53 spins, and we couldn't calculate a priori where that cusp would be. So this is sort of the signature of a dynamical phase transition. I'm running out of time. I was going to tell you about a lot of other summations. I will tell you about one other one that is sort of related to this dynamical phase transition. And also Alex Schickert's in the audience. He's worked very closely with us, including Borkatz in my group, just to observe effects of a 1D phase transition, which we're told you're not supposed to have phase transitions in 1D. Certainly for nearest neighbor interactions, for local interactions, you're not. But we have long-range interactions here. So we might expect to see signatures of 1D phase transition. So here's our favorite Hamiltonian. You'll note that it's no longer inverse power law, it's actually exponentially decaying with distance. And this is because it's technical. We're tuning our laser beams on the other side of all those normal modes instead of the blue side, it's the red side. And the math's a little different. And the trick here is that, well, exponential fall off is a local fall off of the coupling, but we rescale the characteristic distance of the exponential fall off with the number of spins. And in that way, we can maintain long-range interactions that show features of this 1D phase transition. So, like the previous experiment, we don't prepare a given state. We actually prepare sampling of states with different energy when subjected to this Hamiltonian. And how do we do that? Well, we can poke an individual laser beam on each spin and prepare an arbitrary product state. We know what that energy is, we can calculate it, and we can let that evolve. And according to the eigenstate thermalization hypothesis, this is sort of like making a finite temperature. We're synthesizing a thermal state based on ETH and having an ergodic Hamiltonian with long-range interactions. And for different initial states, we see over time that things sort of, in this case we're measuring mean squared magnetization along X, and it sort of settles down over time. So these would be different states with different energy supply. And again, agrees well with theory, and again, I'll defer to Alex here if you have questions on this, he'll be able to tell you a lot more. But the money shot here is really observing the space transition, and theoretically on the right-hand side, we're plotting this observable here is once again, the mean squared magnetization along X, and this is the transverse magnetization along Z. And we have the different energy states that we measured, and different values of the transverse dimension variables. That's what Alex likes to use, G over J here. We can see, theoretically, we expect this sort of second order phase transition to occur right here, where we have a ferromagnetic ordering down here, and then out here is unpolarized. And the data matches very well with theory. A little less so on the transverse magnetization. We're still sort of understanding that. It's a work in progress. But what's interesting here is it seems to be the first observation of signatures of a 1D phase transition. A related experiment that's following on the slide here, several months ago, we observed continued symmetry breaking in this 1D chain. This is a collaboration with Alexei Gorshkov, which will appear in Nature very soon. And my chairman is telling me I only have a few minutes left, and I really wanted to talk about your experiment, which is a different type of a phase transition, where we introduce measurements in a circuit, and with the density, as the density in the measurements gets increased, the amount of entanglement in the circuit goes down, and that's actually a phase transition, called a measurement-induced phase transition. It's akin to percolation phase transitions, and it's very deeply related with error correction. Because if the error rates are low enough, you still see full entanglement. You see in the sense of, say, volume blocking. Whereas if the error rates are very high, then you see area blocking. The character of entanglement as a phase transition. This is really akin to what happens in error correction with fault tolerance. There's a phase transition of being able to handle errors. I do want to make an adversity here for a great collaboration between INQ and the University of Maryland called QLab. There's one whole machine that INQ is working, that Maryland researchers can use, not just in physics, but all across the university. This is one example of that. The next generation of this experiment has to do with distillation of magic states by inserting errors of various intensity in sort of a random circuit here. And again, Michael's really spearheaded this work the last few years. Okay, so I'm just going to skip right to the topological. We simulated SSH Hamiltonian. I'll give you the 2-second version. This is a 22-ion chain, and we show that edge states, when we excite them, they maintain a much longer life than the bulk. And the bulk, as expected from this SSH Hamiltonian, what you have is alternating nearest neighbor isotopes. So, and with that, way out of time. It wasn't clear that a half hour, an hour, but I think that's on me. I'm over a half hour. So I will put one last slide up, which is a little bit of a advertisement of our Duke Quantum Center, which is a fairly unique institute where we're not necessarily doing quantum information science or atomic physics or platform physics. We're doing full stack, vertical organization of quantum computing, from the very top, those that are interested in algorithms or simulations, to those like me on the very bottom, who are atomic physicists and engineers. And we have several systems, 5 or 6 IO-trapped quantum computers that are fully programmable. They have different features and bugs, and we want to model ourselves as sort of a user facility where we can do problems in all walks of science. And this is something, I know there's lots of companies building systems, including a company I co-founded at INQ, but those companies need to create commercial value. This uses very advanced quantum computer, quantum simulation technology for science, which is something companies probably won't do so much. So if you have an interesting application, if you want to design a particular Hamiltonian, please talk about it. And with that, I will just leave the slide of current members of my group in bold here. A few of them are in the crowd. I think Emma and Key are in this conference, and many others you can see remarkably go to companies across the country. And I support from the NSF STAT program in particular for this, but also IRPA and the DoD agencies. Thank you.
Great. So, yeah, just our set of talks, I guess, should be 25 minutes, and then there's 5 minutes for questions. Thanks for the great talk, and, let's take questions. Anybody who has a question, I can try and run up, or you can come up to the 2 microphones in the front of the room. You can just feel free to line up.
Yeah, thanks for a great talk. I think you covered a lot about how ion shots are used for a lot of NIST quantum simulations. The question I have sort of pertains to how you see the prospects for scaling them to full fault tolerance. So in particular, I may have seen a number of experiments that are sort of demonstrating very small error correcting codes on ion traps, but one thing I really haven't seen much of is attempts to look at, say, the resources required to realize classically intractable simulation for application within fault tolerance on ion trap. That's something that's kind of become common on other architectures like photonics or superconducting or even topological. So I'm curious why that is. You think it's sort of a cultural thing, ion traps that they're sort of not looking at that, or do you think there's like aspects of the architecture that aren't worked out to the point where doing that makes sense?
Okay, good question. I can't answer that for my half hour, but I'll skip to the chase. The errors that we have in ion systems, they're not T1 or T2. They're not unknown. 98% of the errors we have are coherent errors. They're control errors. So the last thing I would try to do is go blind with a fault tolerant error correcting code. That's basically, that's sort of being ignorant. With ion traps, we don't need to do that yet. We probably won't need to do it for another decade. So, our group and many other groups have indeed encoded logical qubits, but they're demonstrations. I don't think we'll ever use them. I think we will be able to mitigate errors to a level where we can get well beyond what can be calculated. That would require error rates of 10⁻⁴, 10⁻⁵. That means you should only need if you have 100 qubits, you need about 10 to 4 hours. And that's right around where native errors, like laser scattering, real T1 and T2 happen. And we're not there yet to do that. So it is a cultural thing in ion traps. We don't need it. We just don't need it right now. And I think when we're able to find applications without error correction, I think there will be many more resources that we can port into this technology. Nobody's done the engineering for ion traps like they have in any solid-state platform, so we're just scratching the surface. But when those resources come in, then we can maybe think about fault tolerant error correction, but that's a long way away.
Great discussion. So I guess we're a little bit over time, so I think there's, of course, time for more discussions and debates. You say you're going to go on for a long time with this. So let's welcome the next speaker. So it's Monroe Baker from Princeton University. He's going to tell us about it's the new title, Directly Imaging Spin Polarons in a Kinetically Frustrated Hubbard Model. Oh yeah, there's still lots of room in front. People are saying that.
So, I'm going to be talking about just one of the topics I had on my abstract to keep it more comprehensible. If you want to hear more about work from our molecular microscope, we can discuss it. Right, so to give you a brief overview of the work we do in my group, we are interested in doing quantum many-body physics with ultra-cold gases of atoms and molecules. So what we do is we basically engineer these Hamiltonians, which are theoretical Hamiltonians, which can be used to describe electronic models in condensed matter physics. So they describe materials like these high DC superconductors or moire materials or quantum magnets, where in these materials you have these strong correlations between the electrons, which give rise to emergent phenomena, to new types of phases, with exotic properties that might be useful for technological applications. And we are interested in understanding these materials for these models from a microscopic point of view, to better engineer their properties. So most of what I'll be talking about today is going to be relevant to these moire materials. Okay, so the platform here is called atoms in optical lattices. Optical lattices are basically potentials that we create through the interference of laser beams in the lab. And in this quantum simulation, basically the atoms are playing the role of the electrons in a solid, and the optical lattice is playing the role of the ionic lattice in a solid. So we can think of this as an enlarged model for condensed matter physics, where we blow up the system by about 4 orders of magnitude. The length scales here are on the order of the wavelength of light, so about half a micron or so. And the benefits of this platform are, first, the Hamiltonian we write down for the system is very well understood on the microscopic level with the precision of atomic physics, unlike the crude models that people use for condensed matter systems. And furthermore, we have control over all the parameters of this Hamiltonian, often in real time. So for example, you can control the tunneling of the atoms in the optical lattice, changing the laser intensity or